Okay, so what we would like to do is to create a quantum memory for photons, for photonic qubits. And so what we use is a crystal which is doped with rare earth ions, with praseodymium ions. And typically what we would like to do is that we have a photon coming in, which carries some quantum states, and now we would like to map this photon into our crystal, and the crystal is one of these yttrium silicate crystal, and is doped randomly with some praseodymium ions. So the crystal is transparent to the light, but the light is absorbed now into these praseodymium ions. And the very nice point about these rare earth ions is that they have fantastic coherence properties in the crystal, because they are very well protected from the environment. They can keep their coherence for a very long time. So what we want to do is we have this photon, this qubit. We want to map it into the quantum memory, and then after some time that we can choose, we would like now to take out this photon and have another photon here at the output, which has the same quantum state as the input. The next step after this, what would be to try to have two of these crystals, ideally very far away. It could be in principle tens of kilometers away or even more. What we're doing right now is a kind of proof of principle where they are only a few labs away. And we would like to have these two crystals in an entangled state. So what we want to do is to create actually a photon pair. So we have a source which creates pairs of photon. So this is the photon pair source. And we have two of these pair sources. So one of the photon will be now stored in this quantum memory in the same way as we just here. This one here is red. And the other photon will be coupled into an optical fiber. Is at what we call the telecom wavelength, which means that it can propagate over long distance in optical fiber. And at the central location now between these two, this will sort of interfere here at what we call a beam splitter. So here the photon has 50% chance of being transmitted and 50% chance of being reflected. And basically the role of this beam splitter is to erase now the information about the origin of the photon. So if you have a click in one of these detectors, you know one photon has been detected, but you don't know if it came from this source or from this source. And the same way, you don't know if this photon is now stored in this memory or in this memory. And in quantum mechanics, if you have two different processes that lead to the same results, you have to say that actually the photon is stored in this memory and in this memory, which means that we have actually an entangled state between these two photons, where we have one photon in the memory A and zero photon in the memory B, and in coherent superposition with the other possibility, 0 in A and 1 in B. So this is an entangled state, and it is a heralded entangled state because we know when this entangled state appears. We have a signal that tells us when it appears. Okay, so this is the laser system that we use to address our praseodymium ion in our crystal, in our quantum memory. So we start with a single laser, which is a CW laser, and then we separate it into different paths that we need to prepare now our quantum memory. So we need quite complex sequence of optical pulses. So we use these acoustic modulators that are here and here to be able to modulate the phase, the frequency, and the amplitude of the light to create the pulse sequence that we need to prepare our quantum memory. So we use acoustic modulators, which are here, for example, and here, to make these optical pulses to control the phase, the amplitude, and the frequency of the lights to make the optical pulses. And then the light is coupled into optical fibers over there, and then with the optical fibers it comes here on the science table. where our quantum memory is now in this crystal. So to have all these good coherence properties, we need to cool it down. So now it's about 2.6 degree Kelvin inside. And so the light comes here from this optical fiber and is going now to excite our protodymium ions in the crystal inside this crystal. And this is where one of the nodes of the quantum network will be.